So once you have the analysis tool pack, you can do simple analysis. So when we have data, so as a scientist, you are encouraged to collect data over a few in replicates, not just once, but a few times. Okay, so how many times is enough? As many as possible. Okay, but within uh, practical constraints, within logistic constraints. So if you feel 3 times is enough, then you collect 3 times. Some people, you don't go around collecting 20 times when 5 times is enough. Okay, so basically the how many times you go sampling, how many samples, how many measurements you take depends also on the variance, the variability of your measurement. If after measuring 3 times you find that your data is very near, close to each other, the standard deviation is very low, then there is no point increasing the number of measurements. Okay, but even if you measure 10 times and you still find that the standard deviation is very big, then you may have then it is advisable to continue measuring so that at least you will have a better measurement of the median, the central tendency of your data. Okay, just so that you get a more accurate measurement. So for example, whenever you have data, for example, if you measure over a few times like this, so it's good to know your mean, okay, and the standard deviation. Of course, if you know your if you can remember your formal equation, you can just type average, highlight it, then you get your average, right? Or if you want, you can get your standard deviation, highlight it, and then you get your standard deviation. But Excel also can calculate for you. If you use data analysis, here you're looking for descriptive statistics. Okay, so what you can do is you can say your input range. So we place the labels in the first row. So the output range, we'll place it here. Then we want the summary statistics. Okay, so that will give you your mean, your standard deviation, okay, also your count. So this is useful if you have a lot of data, many columns, and you can just highlight all of them and generate the sample statistics. Okay, so when you collect data, you realize that sometimes your data is not exactly normal. Okay, so sometimes you have positively skewed and negatively skewed data. So if you were to ask to draw, so this would be what? This would be positively skewed, and this would be negatively skewed. Okay, so this one, the median and the mode is towards the lower end. Okay, the median and mode here is towards the higher end. So this is positively skewed and this is negatively skewed. Okay, but when you draw histograms to describe your data, you may also see different types of distribution based on the sharpness of the top. Okay, so you can have, so leptokurtic is very sharp, platykurtic is flat, and mesokurtic is your about your normal distribution. Okay, so this is mesokurtic, platykurtic, and this is leptokurtic. Okay, so this question, why should count data be transformed before statistical testing? So for microbiologists, most of the count data, you'll be collecting a lot of count data. So why do you, it is always advisable to transform your data before you carry out statistical testing. Why do you think it's so? Parametric statistics, and this parametric statistics assume that the data you are using is in a normal distribution. Okay. However, count data is not normal. Okay. If you realize your counts, if you're doing CFU per mil, it's usually like times 10 power 2 times 10 power 3. So it's not normal. It's skewed, probably negatively skewed. It's, because it has the power 2 power 3 high counts, but it doesn't have the small counts. So it's not normal. So because of that, you are advised to transform it. Usually we log transform it before we use it for statistical testing. Okay. So we transform it because the CFU per mil data is not normal. Okay. Okay, so let's start with a few simple statistics. So you have here to compare the mass in August and September. So comparison of measurements done in August and September. So what kind of test do you think we should use?
ttest.
Okay, so let's do a t-test. So t-test, can you assume equivariances? Okay. So variable 1, variable 2, hypothesized mean difference is 0, which means we are hypothesizing that there's no difference between them. We replace the labels in the first row, then we output the range here. So we have data here. So this shows the mean and variance of the measurements carried out in August, and this is the one carried out in September. So the hypothesis mean difference is 0, your degree of freedom is 18, your t-stat is 2.7. Okay, the t-stat is 2.716. It doesn't matter whether it's positive or negative. It's negative here because your September is higher than your August. That's all. It's the value that is important, not the negative or the positive sign in front. Okay, so now you have this P and T. critical at 1 tail and 2 tail. So usually we use 2 tail because 2 tail is more stringent. Okay, so if it's significant at 2 tail, it will definitely be significant at 1 tail. Okay, so P is the probability. So the probability is 0.01. That means, does that mean it's significant or not significant difference?
Not significant.
Huh? Is it significant or not significant difference? You see, when the probability is 0.01, that means the hypothesis is there is no difference. Okay, the hypothesis is there is no difference. But the probability now is 0.01. It's less than 0.05. Means it the distribution is it is at the extreme end of the normal curve, normal distribution. So when the p is less than 0.05, it shows that the difference that you observe here is not due to it's not due to it is not due to random sampling. Okay, so it is when the p is less than 0.05, it means that what you are observing is highly significant. What you're observing shows that the difference is significant. Are you all following?
Yes.
Is everyone following?
Yes, doctor.
So when the p is less than 0.05, that means your observation shows that what you're seeing is not 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 normal. Okay, it's not is highly significant. The difference is highly significant. Okay, so this is the t critical. This is the value that you get from the textbooks, from the statistical tables. So this is actually not so important. What is important is this, where the p is 0.014. What is also important is your t-stat. T-stat is 2.716. Okay, your df is also important because these are the values that you will report in your thesis. When you report in your thesis, you report your t-stat, your df, and your p. Okay, so the p is less than 0.05. That means the difference in August and September is the past window. Okay, it's a free software, so there are some quirks that you have to learn how to adapt to. Okay, so let's just see whether you can get this. I'll just copy this data. Okay, so in order to paste the data inside, first I have to check out the column attributes here, then paste it here. Okay, so once you've pasted, you can highlight it, and then do a these are the univariate statistics that is available. Okay, you can also do summary statistics. So when you do summary statistics, it will also give you the same the same data that you get with, in fact, with Excel. So you have your sum, your mean, standard error, standard deviation. Okay. Of course, there are more than what this is, more than what Excel can do. Okay. So what we want is we want to do we want to compare a t-test. Okay. Can you see this window?
Yeah.
Okay.
Yeah.
So the t-test shows your n, your mean for August and September. Okay. Then the variance. The difference between the means are 0.88. Then this is the t-stat, 2.71. Then this is the t. Okay, so it's 0.014. The critical t value at 0.05 is 2.1. So your t is larger than the critical t value. That's why your probability is, the p is 0.01, is significant, highly significant. Okay, so that shows the differences that you observe in August and September are highly significant. Okay. So next you have this. You have to compare the mass of birds from 4 different nest situations. Okay, so if you have comparing, so if you're comparing from 4 different situations, what test do you think you should use? Data analysis, okay, single factor ANOVA, input range. You group them by columns. The label is in your first row. The output range, you just have to, let's place it here. Okay, so that gives you your, so p value is less than 0.05. That means the mass of birds that you measured from situation 1, 2, 3, 4, they are not similar. Okay, they are not similar. So ANOVA tells you that they are not similar, but it doesn't tell you anything more than that. Okay, it doesn't tell you which one is not similar. Just you are comparing 4 groups, and that when you compare them, when the p is less than 0.05, that means they're not similar. Some of them are different, but you don't know which one. Okay, so in situations like this, then you realize you need something more powerful. Okay, let's try pass. We do the same thing. I click column attributes so that I can paste it here. Okay, let's try it. So now I'm doing ANOVA, several samples. Okay, so the probability that they are the same shows is less than 0.05. That means among the 4 groups there are differences. Okay, so the results are from past is the same as the results from Excel. However, if you look here, you have turkeys pairwise. Okay, turkeys pairwise. So turkeys pairwise comparison will show you which one is different. Okay, so that gives your data, your analysis more value. ANOVA there's difference, but it doesn't tell you which one is different. So for you to conclude which one is different, you need to do a turkeys pairwise comparison. Okay, sometimes you will see this as turkeys HSD, or honestly significant difference, HSD. Okay, but you only do turkeys pairwise comparison if ANOVA is significant. If your ANOVA is not significant, there is no need to do turkeys pairwise comparison. Okay, and you enter the formula one by one. But you have this software, so I don't think you should be doing that anymore. Okay, use this pass, then you can get the turkeys pairwise. Okay, let's see how we interpret this. Here you can see there are two groups here. The value here shows the Q. So turkeys value is shown as Q. ANOVA is F. Students t-test is T. For turkeys HSD is shown as Q. So Q equals 3.733. Okay. So when you compare situation 1 and 2, the Q is 3.733 and the P is 0.05645. So it's more than 0.05. That means statistically there is no difference between 1 and 2. So the highlighted ones here shows that situation 1 is different from 3, situation 1 is different from 4. Okay? Any questions?
No, doctor.
So do you understand how to use PASS and Excel to do ANOVA?